Hello. So first I'd like to acknowledge the organizers for having me here. It's very nice. Thank you. I will indeed be talking about 2 or 3 developments in helping geophysicists understand things like Earth structure via the application of some new techniques in mathematics. Some are new, some are old, but have a new spin on them. And all of them have resulted in powerful algorithms that have been fully developed and tested and that are now in the process of being used for a variety of applications. This is, of course, not work I've done by myself. There's too many collaborators to acknowledge them individually. But if you need to read up more about the material, of course, you'll find all of these people. So 3 main subjects for me today here. First of all, I'm going to talk about something called Slepian functions. And as I was writing this to Seth, he told me that he used to play with Slepian's kids. Now, you'd be the one telling me, is it Slepian or Slepian? Because some people say the other thing. That's what I've been saying, so I've been guessing that right. A mathematician at Bell Labs who passed away, I think, about 5 years ago. And the second thing is I'm going to talk very briefly about wavelets on the sphere, and not a full theoretical introduction, but a very practical construction that we've been using to learn about the scale and space dependence of anomalies in the Earth, seismic anomalies, for instance, and then also to use this sort of a basis to promote sparsity, by which I mean that we have been designing and using algorithms that directly try and recover terrestrial structure in terms of a finite small set of basis functions. And the name of the game here is to tackle very large problems, but to try and find some very small set of basis functions whose coefficients very well represent the Earth and thus satisfy the data in the traditional sense. So I realize that this is probably new to most of you. However, there are some strong connections here in the engineering literature since in about 50 years of a history. So I'll just start by saying that in one slide what I mean by localization in this sense. So in a nutshell, it's the realization that a function, a signal, cannot be band limited and space limited at the same time. Anything is never band limited because we always have a measurement device or a transmission device that does not have infinite bandwidth. So we need to stop somewhere. And even if it were non-band limited, we could only compute it to a finite bandwidth. So we need to stop somewhere. And given that, we're faced with this fact that signals that are band limited are never local, strictly speaking. So what we're going to try and do is we're going to try and find an optimization of those dual constraints of band limitation and spatial concentration or time concentration in one dimension by finding the set of Slepian functions which are either band limited, strictly band limited with optimal spatial concentration, or conversely they might be precisely space limited, in other words vanishing outside of a finite support, but that will be concentrated as much as possible in the bandwidth that is available to us. And before I even go on, I should mention this connection to Slepian, who was an engineer working for the phone company. And phone lines are band-limited transmission devices. And of course, what the question that he was concerned with is how much information can you really send over, say, 1 minute of a phone conversation. It's not an infinite amount of information, and he developed some powerful techniques and tools to characterize just exactly what is the information that can be contained in such a temporally and spectrally limited domain. So for us, of course, the spatial domain of interest is the Earth. Any combination of patches that we're interested in, either over which we have data and that we want to analyze, or areas of which we have no information. These could be disconnected, closed surfaces, such as these regions R1 and R2, and they could, of course, also be very nicely symmetric polar caps or double polar caps, which are very useful in satellite data acquisition, where these are typically limited or have gaps of coverage in such domains. And the last image, if it isn't a double polar cap from satellite geometry, might be the area of coverage that we get from imaging the cosmic microwave background radiation, where the central band is the thing that we want to cut out, as opposed to with the typical terrestrial satellite, where the central part is the area over which we fly. So boxcars, of course, are the prime example of perfectly spatially limited functions that have infinite leakage into the broadband spectral domain. And I'm going to just give you some examples before going into how they're constructed of what these Slepian functions are. Here is a collection of functions that are all band limited to the same spherical harmonic degree 18, which is a very low number, and they're optimized to concentrate in a spherical cap of a colatitude 40. And so the first one is almost perfectly concentrated, but of course it is tapered. It's sort of a hat function. And the second one and the third one and so on, they together form an orthogonal set of functions that all share this property of being perfectly band limited, yet optimally spatially concentrated. And so you'll see where I color code the black lines is the area of the cap. The gray lines is the unavoidable leakage that you get by having a strict band limitation. And the first few sets that have these lambda values as a measure of how much energy actually is in the cap is very, very close to 1. And then as you go on, it gets to be very, very bad. And so the last one there is almost not concentrated in the cap, but leaks completely outside. So the trick here is that by this transformation, we have the same number of functions as contained in all of the spherical harmonic space of L equals 18, bandwidth 18, yet the first 12 or so in this case are very nearly perfectly spatially concentrated. And if we want to study processes on that patch, we'd use those, and we can safely ignore the other ones because of the fact that their spatial concentration is so low and their influence on the solution is so minor. Okay, the traditional indices of the spherical harmonics I call L for degree and M for order. And the beauty of the spherical cap is that there's a complete decoupling of the orders, which gets lost as the region becomes of an arbitrary description. But so thanks to this, this decoupling of an order by order structure, we can in this case solve a vastly simplified problem order by order. And so in the spectral domain, this is the converse here. Here the axes on the y-axis are decibels of power of these functions, and the same x-axis is again degree. And the black line here shows you the area down to L equals 18 in which these former functions are perfectly concentrated. And should we have truncated the spatial domain, we would have gotten leakage in the spectral domain, and that's shown here by these gray lines. And so you see that at L equals 18 in almost all of these cases where the concentration is once again very good, as by the high eigenvalues, we get power reductions of over 20, 30, 40 decibel. So these are now effectively band limited in this case and effectively space limited in that case. And we can go back and forth between the spatial and the spectral representations, of course. So as a more of a tutorial overview of where these things come from, I mentioned the work by Slepian. And so in one dimension, quite literally, Slepian solved the following problem. He said, give me a signal, g of t, that is going to be perfectly band limited as being given by a Fourier transform of some big G of omega, strictly confined within these upper and lower limits minus w to bandwidth. And so you try to stick that signal, which is perfectly band limited, into a short time interval, that's the 1 minute of the phone conversation, where the time interval of interest is big T. And quite simply, Slepian proposed a quadratic energy criterion, which is this lambda, says, give me the function space that maximizes this spatial concentration for a given band limit, and that's equation 2. And when you do that, then you find that these functions G, the Slepian functions in one dimensions, are eigenfunctions of particular integral equations with that kernel, which is a very well-known sinc kernel, which depends on the product of time and bandwidth. So it's the joint footprint in temporal and spectral space that determines how many functions you can find that are of a certain concentration. So that blue thing is the kernel in this case. In 2 dimensions, which Slepian actually only ever solved for completely symmetric cases, the situation is completely analogous. So now we get a signal G of a spatial 2-dimensional domain X, or 3-dimensional domain, that is once again completely given by its Fourier transform on some finite domain K, which is less than the entire spectral space. And let's try to fit those with energy into a spatial domain of interest. Completely analogously, we're going to try and optimize the integral of the energy over the region R of interest compared to the complete space. And those functions, of course, also satisfy an integral equation, and the kernel there is a slightly more complicated but yet similar blue thing that's there in equation 6. Now finally moving on to the sphere, that's the area that Slepian actually never touched, and this is where it becomes interesting for geophysics, which is why we set out to solve that problem. Same thing here. Now a band-limited function for us is something that has a Fourier representation as a finite discrete sum over spherical harmonics. The G sub LM are the expansion coefficients, the YLM is your choice of normalized harmonics. And we're trying to now concentrate them on a spherical patch of interest, a 2-dimensional but in 3D space patch of interest, such as Greenland or Africa. Very same thing, concentrate the energy into the domain of interest, maximize this property, and what you need to solve is this integral equation. Now here we go again with the blue kernel. It's the same type of an integral equation. So the 3 blue kernels there, at the end of the previous slides here, each of these actually are band-limited delta functions. If you take the blue kernel there and you let L go to infinity, you have a delta function. And similarly for the 2D and 1D case. So what we're getting here is a basis for a function space. And so these Slepian functions are bases in this function space of things that have so-called reproducing kernels that are band-limited delta functions, if you will. The traditional class of functions, which are just sort of square integrable functions, are all living in a space with a reproducing kernel of the delta function. But if we're willing to, or forced to, have a band-limited representation of our functions, we now have a completely new space. And so these equations show that that is the reproducing kernel that sets up this space. I mentioned the case of symmetry. In the case of symmetry, everything is beautifully analytical. In the case of geographical areas of interest, you solve these integral equations. And so this is a case for Africa. We're once again down to L equals 18. Normally, you wouldn't get functions that, of course, pile up in Africa. You would get spherical harmonics, which are wiggly functions everywhere. But by this optimization construction, we get the first few members here that live in Africa. And you see the first one is a roughly symmetric sort of radial type basis function, and the second one and third one and fourth one, they are the additional elements that you need to represent structure in Africa. And the things that stand out is that all these functions are band limited. They're all orthogonal, both on the entire sphere and on the domain of interest, which is very attractive to solve problems. And of course, if you were to represent signals in Africa by just radial basis functions, you'd have to move around to try and approximate structure over Africa. But in this case, you just continue to combine elements from all of these functions, and all together, they're a complete basis for band-limited functions anywhere on the sphere, and they're an approximate basis for L2, square integrable functions on the domain. So immediately, I think we see that these are very good candidates to approximate signals on limited domains where we are restricted either by observation or by computational demands to stay within a certain band limit. So in summary, the spherical harmonics that seismologists and geodesists and everyone else use are so attractive for global problems because they are orthogonal on the entire unit sphere. You take one of them, YLM, you take another one, YLM prime, you integrate their product over the entire sphere, you get ones or zeros. That's no longer true, of course, when you restrict the domain of integration to the region of interest. So you've lost this important property of orthogonality, which is very detrimental to solving inverse problems and which leads to very poor statistical performance, not to mention efficiency. And the key property of these Slepian functions is that, well, we are going to call that lack of orthogonality, this gram matrix, if you will, of these elements of the spherical harmonic basis, we're going to call that D, which itself is a spectral matrix, spectral in both dimensions. And we'll just diagonalize that and find its eigenfunctions. And its eigenfunctions are the expansion coefficients of the Slepian functions. And by that token, by construction, they're orthogonal both on the region R and on the sphere. And they satisfy these two other properties that I introduced earlier, namely the optimal quadratic concentration and the fact that they're, of course, the solutions to these particular integral equations that I also showed you. And the key now here, where we're going back to Shannon type of information theory, or to Slepian type of one-dimensional studies, is that asymptotically, these Slepian functions are also approximately only dependent on the combined product of available bandwidth and the area of the region. And so that leads to a special number that we've called the Shannon number, which gives us the dimension of approximately space and band limited processes on the sphere. And that is the combination of the complete dimension of the spherical harmonic space, which is the band limit plus 1 squared. That's the number of L's and M's that are in the expansion that are needed. But to represent signals in Africa at L equals 18, you'd literally need all of these elements to represent the signal. But because of the spatial restriction and the new construction of these Slepian functions, we get by with an approximate dimension for Africa that is reduced by A over 4 pi, which is the fractional area of coverage of interest. So where one needed to have 19 squared functions to represent Africa, we can now get by with whatever the fractional area of Africa is, let's say 5% of those functions. And so that concludes this loop with the papers of Slepian and Landau and Pollack, who wrote papers on what the effective dimension was of approximately time and bandwidth concentrated functions. And so that for us is now a space bandwidth product. So spherical harmonics are well known and beloved by most geophysicists as these global functions. And here is a selection of them over Africa, just evaluated on a little rectangle centered on Africa for various or random combination of degrees L and orders M. And so, of course, you see that at low degrees, they're not very wiggly. At high degrees, they're very wiggly. The orders tell us how the orientation, the pattern of nodal lines go. But the main thing to notice here is that they're not particularly suited for any regional feature because they're just global functions. So that does very well to represent global signals. In this case here, I'm showing the an expansion of the lithospheric magnetic field, quite literally taken a model from satellite data analysis, nulled out all the coefficients that give us a strong red spectrum for the Earth's core field, and above degrees 17 to 72 here, this expansion on the left is the radial component of the what we interpret as a lithospheric magnetic field. And on the right, it shows you an arranged diagram of the expansion coefficients in the spherical harmonic basis. So there's nothing in that lower wedge because that's where the core field has been taken out. And you need about 5,000 numbers in this representation to get to a resolution of this map. And this works very well, and people have been doing it for ages. But now I'm going to notice that circle over Africa, which has a particularly interesting anomaly, which is centered over Bangui, the capital of Central African Republic, I believe it's called. And let's try and represent that in spherical harmonics. So here I find the expansion for that Bangui anomaly in spherical harmonics, and once again I need about 5,000 numbers to represent it. And I now need to choose those spherical harmonics such that they perfectly reproduce the anomaly of interest in the region of interest, but now they are perfectly canceling each other out outside of Africa. And the reason that the lower part, the lower wedge of the crustal field is filled is to achieve this cancellation. And all the colored squares, again, are the roughly about 5,000 coefficients needed to get this local representation. So immediately you see that this is not a very good basis for local problems, because you need to pick and choose them so that the area of interest is well represented. And from an inverse modeling standpoint, if we're just interested in Africa, or if we just have data in Africa, we would, of course, much rather invert not for 5,000 coefficients that all need to conspire to produce the right model, but rather for something smaller. So here we go. Here is the transformation now. Both panels here, once again, are literally the Slepian functions. Both panels are identical. The only difference is a judicious rotation of one matrix to the other that highlights more of the structure. But so both panels show the eigenmatrix of that gram matrix of the spherical harmonics. And so every column is a spherical harmonic expansion, each of which is the expansion of a Slepian function in the old basis. So by taking whatever we have in the spherical harmonic basis, computing this optimally localized basis for, in this case, Africa, and using that as a transform, we get the Slepian functions. And that's what they look like for this particular problem in Africa, centered on the spherical cap. The first few elements are now beautifully localized, and because of the symmetry of the spherical cap, once again we have this, we retain the notion of a spherical harmonic order, and so we can just conveniently label them, and we completely understand the symmetries in it, where we're going from a sort of a zonal pattern in the first one to two bilobate patterns, which would be the m equals 1 and minus 1, and then so on. And so they continue to cascade down to where we're going to end up having functions that live everywhere but in Africa, but the first few here are beautifully localized inside it. And so whatever we're doing, whatever you are doing with spherical harmonics, if you want to localize this, all you need to do is compute this type of a matrix and stick it at the right part of your code, because it's just a linear transform of harmonics, and you get these localized functions. So that's now how the expansion of the Bangui anomaly looks like in Slepian functions. Just about 100 of them, as opposed to the 5,000 harmonics, give us perfect recovery of structure in Africa. And the reduction of 100 to 4,000 is exactly by the fractional area of the of what Africa is with respect to the full sphere. So now back again to a traditional inverse problem. We'd rather solve for a handful of coefficients right in the basis that is orthogonal and that lives right in the space where we need it, than to try and come up with complete spherical harmonic models. No, so what this is an approximation problem. This is a no-noise approximation problem. And so the perfect approximation is all of the Slepian function, and there's no gain. The very, very, very good approximation is by the first k functions, because all the other ones have so little information about Africa that you can ignore them, and you can put exact bounds on that. For a real inverse problem, of course, which is noisy, you need to combine and find a truncated expansion where you will need to decide based on signal to noise ratio where to stop. And that is definitely not at k, but it's certainly not all the way at the end either, depending on signal to noise. So, you know, that's us. That's us trying to come up with new bases that efficiently represent global or local signals. But how about nature? And I figured let me give you one example of where geophysics actually gives us something close to the Slepian transform, and we really draw a lot of benefit from using it. So that's the question I'm trying to address now in the next 2 slides. Which processes in geophysics perhaps are very well suited for this? And so it turns out that earthquakes are. This is the top line here is for 3 distinct moment tensor earthquakes, shown at the top there, 6 elements, they show you the patterns, is the expansion of the gravitational potential perturbation due to earthquakes centered at this point. And so people don't usually look at this. People usually look in spherical harmonics at the very, very low degree gravitational potential perturbations. But there's nothing stopping us from, if we can make seismograms of the displacement, to also look at the gravitational potential perturbation. And that's what the top slide is. And after doing that, of course, it's easy to notice that the first 3 types of Slepian functions are very, very similar to it, which suggests that if we look at raw data collected over the globe of gravitational potential perturbations, that if we project those onto the Slepian functions, that we might pick out individual elements of the moment tensor and thereby study large earthquakes from spaceborne gravity, time variable gravity. This is what we've done here for the Sumatran earthquake and a few other ones after that. So in this example, I'm taking a time series in the blue dots here, raw data from GRACE. Raw thereby means it's somebody's model of what the satellite has measured as a function of time from 2002 to 2009. And instead of representing it in spherical harmonics, I represent it in the 2 pairs of -1 and +1 Slepian functions. And you see that immediately that right at where the Sumatran earthquake is, there is a big jump, because in this space, the signal is really very sparsely represented by it. Of course, the basis is completely rotationally invariant, because all we're doing is optimizing the quadratic energy in the cap. And so we rotate these functions until we maximize the signal on one channel and minimize it on the other channel. And then we can make 2 measurements, one of the signal to noise for that particular component, which would be panel C, or in panel F, we would have the jump related to the earthquake, the co-seismic gravity change, and the strike of the earthquake in this case, by looking at the alignment of the function with the Sumatra-Andaman trench. And so this opens up a way of, by simple basis projections, studying where in space certain geophysical signals that are regional in nature and that are very well represented in this basis are being concentrated. Okay, so as a tutorial nature, how to construct the functions. We wrote this up in a publication in 2006. How to use them for a linear inverse problem of determining the source of anomalies at satellite altitude. We wrote this up in 2006 also. And then for a quadratic problem in the data for how to do power spectral analysis, using the Slepian functions not as a basis but as a smoothing window to do multi-taper analysis. We wrote that up in 2008. So unless there's questions, in which case I'd be happy to stop, I'll give you a few elements of some more localizing transforms. And I know I only have a few minutes, but we started a few minutes late. So, so all of this here required some prior knowledge of where to look. We can employ it in detector mode, a spherical cap, we can rotate it to any portion on the sphere we like, but then we'd have to try all combinations. If we know it's in Africa, we'll look in Africa and so on. But so now we really would be drawing some benefit from using localizing transforms that don't necessarily need to know just yet where the signal is big. And I'm going to quickly say about wavelet transforms that they're made out of scaling functions and wavelets. Scaling functions give us smooth approximations to the signal. Wavelets give us detailed approximations to the signal. And putting all together in some expansion here in one dimension, we get a multi-resolution representation of the signal, which is the sum of over all these wavelets and scaling functions at particular locations and scales. And here are some examples that I hope are probably familiar to you. Now, what we try to do, and here's some algorithms to do it. So what we're going to try and do is we're going to try and treat the Earth not as a sphere. We are now interested in imaging the Earth with seismology as an actual volumetric object. But building wavelets on the sphere is hard, and it's a subject with a long history. And so we're going to cheat, and we're going to try and use a Cartesian transform in 3 dimensions and map it on the sphere and see how far we get with that representation to come up with spherical wavelets. So we're going to take the depth dimension of the Earth in a transform. Let's keep it simple and use a lowest order hard transform. And on the surface, let's do something a little bit more involved using, say, the Debussy transform. And we're going to build a cube sphere, which I'll show you in a minute, which has edges, and we'll take those edges into account. If not, we'll get artifacts. And so this thing is called the cube sphere. This cube sphere is a very popular numerical grid to solve PDEs on the sphere in atmospheric science and seismology for global wave propagation is very widely used. And so the main elements of its 6 faces, and then in depth, but they have boundaries, are illustrated in this picture here. So mapping Cartesian wavelets on a sphere is basically as simple as doing this spherical to cube spherical mapping. And here are some examples of the wavelets at different scales, and one scaling function in the first panel, and of various constructions. The reason that we're doing it is that you can open a book on numerical recipes and get the Cartesian transforms very easily, including the special boundary filters. And the mapping is very easy to do, so now you can do wavelet transforms on the sphere without much of a headache. So as an example, I'll break down the topography over Africa. In the middle is a map of it. On the left is the map of the coefficients, and on the right is the histograms of the negative and the positive expansion coefficients of gravity. Now, of course, to represent the map, I need all the coefficients. But the notion of sparsity comes back by first doing the transform and then looking at where the information is living and thresholding out by taking them away the very small coefficients. And the beauty of the wavelets is that it projects the useless structure onto a great number of small coefficients and keeps the high energy structure into a small number of useful coefficients. So here's the examples of throwing out 25%, throwing out 50%, throwing out 85%, and you can keep throwing out until you're no longer satisfied by your favorite misfit criterion. But in this example for topography, with 85% of the numbers set to 0, you still have close to 100% of the information retained. I'm going to skip, but you should be aware that we've also looked in detail at how seismic models hold up under this procedure, and the fact that we can use it to study scale and space-dependent heterogeneity in the Earth. And then I'll save 2 more minutes on, if Dave gives it to me, on how to put this into an inverse problem. So we have a basis. Let's try to use it. The traditional geophysical inverse problem, of course, hasn't changed over the ages. It is to try and get back from some functional that has changed what we call the model, but others don't. The signal, let's call it S, that's been noisily observed, and we need to go back to the hypothetical truth. Traditionally, we're doing this by minimizing quadratic misfits in the data space, and we add regularizers, which are quadratic norms of whichever basis the model is in. And this is known as the classical Tikhonov regularization approaches. But so in the last few years, combination norms have come up in importance here. And so if Slepian bases are so sparse, if wavelet bases are so sparse and are so successful at representing Earth structure with a few components that are important, we should try and target our inversion to find that. Now, the number of coefficients you could call the L0 norm, if you will. But what a variety of mathematicians have worked out is that under the right conditions, by looking for the minimization of the data misfit, the traditional least squares term, and adding an L1 norm, which is the sum of absolute values of the coefficient, you can get iterative methods that get very close to the sparse representation of the unknown model that fits the data to the same level. So I have a toy example here of a sparse signal, which is just 10 components out of 100 that are big. And now I have a random matrix, which is my forward model. This isn't seismology, this is a bunch of random numbers, and then there's noise added. And so the data is F times S, this matrix times these 10 peaks. And if you use the traditional Tikhonov squared square regularization, you get a model that looks like this. And if you use these new methods that have been coming up, you get a model like that. And so what I'm arguing here, and what we have argued, is that these methods now are ripe to be used with spherical wavelets for seismology, because we can be confident that our wavelets will be very good at representing unknown structure, and we will be confident that we have algorithms to target it without prescribing where those wavelets should be big. The only knowledge that goes in there is to saying, we think the signal is sparse, and we know it from prior observation that there are going to be a few important coefficients. Let's find those. And that is the main message here. And we have just published a paper where we're showing this in an example. Unknown, this is the known structure with some holes knocked out to make it more interesting. This is a path coverage from seismology, which is a realistic set of 8,000 or so surface wave paths from published model. And this is how we recover it using the thresholded iterative L1 plus L2 misfit algorithm. And so we see we recovered the structure very well, and we do not leak very much into the areas where there should be null structure. And we do that with just a few components of it. So that's my last slide here, is how the misfit norm behaves for this algorithm. You start somewhere, and you first minimize the data misfit. And then after you've reached a good point, you're sort of backtracking in this algorithm and tossing out coefficients that after all weren't needed to converge at a solution at the target 1 reduced chi-square here, which overall has just a handful of coefficients, several hundreds, as opposed to the many thousands that are potentially useful in representing volumetric Earth models. So that's basically it. There's a lot of new activity in localization, building on work in engineering in the 50s that's been used for spectral analysis and function representation on the real line, and we've brought that all onto the sphere. There's been so much work on wavelets that all of these algorithms are ready to use, and what sort of has been missing is to make it easy on the sphere. And we propose to just use a map of Cartesian to cube sphere, which we've shown to work very well. And then, of course, combining all that with the recently expanding field of algorithms to try and find the sparsest representation for inverse problems that satisfy the traditional data misfit norms, but also seek to build a model from just a few components. All of these things now we are now putting together to, well, hopefully great effect in the future. And that's it. Thank you.
Do we have some questions? Yes?
So, one of the miracles about the band limiting operator, at least the one you first started to talk about, is that it's a long-range thing, but yet it commutes with the differential operator. That differential operator has eigenfunctions that correlate spherically. So my question is there a sort of analogous structure on the sphere for spherical harmonics?
Yes, there is. This only applies in two special cases. One of advanced symmetry, and the single polar cap, which is rotationally invariant, that I showed in the first cartoon slide, it applies to that, and also for the double polar cap. So this is one of the key portions of our 2006 paper where we were looking to find this operator because we knew it existed in 1D. And it turns out that Fernando Grunbaum had already solved that problem in the 80s. And those are the only two cases that we think are happening. And we're now trying to look if similar structures exist for, say, vectorially vector-valued functions where they would be very useful also for geomagnetic research. But yes, exactly. This exact analogy for it. We have a variety of choices depending on symmetry and desired algorithms. For the most general case, we will construct by numerical integration the gram matrix of harmonics and diagonalize that. Then there is no more of any equation to be solved than that. For the case that was just mentioned there, because of this commutation relation of the integral with the differential operator, we transform that to the spectral domain and solve that. And so that's the exact analogy of the Slepian's problem. But we can equivalently, and have done it, in fact we used to do it until we discovered the commutation, solve the actual integral equation. And so yes, any of those three approaches are being used, but of course where the best one is the simplest one, we just have been sticking to that one.
One more, the last one.
How are you dealing with nonlinearity?
In where?
I say in your model. So here you have a linearization that you're using to pull out your good basis functions. You have a nonlinear problem. The good basis functions are dependent on the nonlinear.
Yeah, so far we have not been dealing with that, so that's an open question.
Okay, if there are no more questions, are there any questions from the people?